Okay, so this is to finish lecture 2 of gas laws, and it's just a quick section on how do gases behave ideally and non-ideally. So what does the word ideal really mean in like our everyday life? What are we saying when we say something's ideal? Average? What it's supposed to be? Yeah. How you want it. I like that one. Yeah, what you want it to be. So years ago, I made a horrible analogy to a person in class, which they had talked themselves up to be this guy who talked to all these girls, and he always was talking about girls in class, and I have incredible hearing, so I always heard him saying these things. And so when I got to this lecture, it just made sense to say, like, well, ideally, he would be a great boyfriend, but in reality, he's not. And then the class got really quiet, and I realized that I must have hit like a very soft spot for him. So instead of apologizing, I dug myself into a deeper hole, and I was like, well, why don't you just go cry about it under the desk? And then it got really quiet. And I said, I'll never do that to a student again. That was just awful. And I later apologized, but to my defense, he had constantly been talking about all these different girls, and he was giving them code names, and like, I hear these things in class, so rightfully so, you're not an ideal boyfriend, right? I would never tell. So instead, I just talk about it every year.
Can you give initials?
No, rhymes with Pike Perfy.
I don't recall.
You don't recall that. So anyway, ideally, he seemed on the surface like this great guy because he was smart and handsome and an athlete and all these wonderful things, but in reality, not so much. So ideal gases behave like we want them to behave. We think they're behaving that way, but in reality, they're not. So they only behave a certain way under certain conditions. But then when we deviate from those conditions, we can really no longer use the PV equals nRT equation. So this equation we use all the time, and we don't even care if they're ideal or not ideal. We're just going to use it and say it works. But when you guys go in the real world, like, that's not going to be okay if you're not at essentially room temperature. So when they don't behave ideally is when they're under high pressures and low temperatures. Either you're going to memorize this because you don't really care about the science, or you're going to understand what happens and why they deviate. And it's mostly because they now interact with one another. So in this equation, there's going to be two things that get messed up. The first is our pressure assumptions and our volume assumptions are going to change. So right now we assume, we'll talk about volume first, that in the space around us, remember we talked about there's only 0.0084% of molecules that are actually in this empty space. So everything is just empty space. We ignore the 0.0084% because it's so insignificant. Do you agree? When we take into this calculation, we are saying the volume is empty space. But what if it's not? So right now, if I were to take the volume of this room, I would do length times width times height. I'd come up with the volume of the room, and I would ignore the fact that you're in here and desks are in here and everything else is in here. I would just give you the volume of the room, right? But what if instead I compacted you into this really small cabinet over here? Now your volume is going to take up a whole lot of space, right? So now the empty space volume in a small cabinet is really much less than it actually we perceived it to be. Do you understand that? I'm taking stuff and now I'm cramming it into a volume. Now the volume that you occupy becomes very significant. So if this is my space where my molecules are, 0.0084%, and then I smash them like this, now the space that they're occupying in this little opening is more significant. Do you get that? So we have to subtract out their volumes to come up with the correct volume. Now, before the curriculum changed, you used to have to actually calculate that. All this is theory. So all you're going to get on my exam is a theory question. I promise you I'm going to give you one that asks you specifically to discuss the issues of non-ideal behavior under high pressure and at low temperatures. What specifically is happening? So we have to account for the volume of these molecules just like I would have to account for your space occupying a cabinet. Okay? So it says here, under high pressure, greater than 5 atmospheres, and then at low temperature. So we're going to touch on both of those. So let's first look at this graph here. It's just describing to you, if we had 1 mole of gas at ideal conditions, our ideal gas would plot perfectly on this line. the ratio of PV over RT would be straight line for 1 mole of gas at all of those pressures, and then it's showing you here how as soon as you go past 5 atmospheres, the gases all completely deviate from ideal behavior. So they're all over the place, and I'll talk about specific gases and how they deviate more than others in a little bit. So really, it's just 5 atmospheres isn't very much, right? As soon as we go past that, we deviate from ideal behavior. This one is showing you the same exact issue for just one gas, nitrogen gas. So as soon as we deviate pressure here, as soon as we go higher pressure, it immediately deviates from ideal behavior. But if you notice, at the higher temperatures, I'm coming back down to ideal behavior. So let's talk about why does that happen. So at high temperatures, what are the particles doing? As soon as I say temperature, you think kinetic energy. So high temperature means what happens here? They are going faster. They're going faster, right? So if they go faster, you need to remember fast molecules move further apart. That's it. They always ask that on the AP exam. What happens when the kinetic energy increases or temperature increases? The particles move faster and further apart. They now move further apart. I don't know if they're in the same container that's really true here, but they're moving further apart. So they really have no interactions with one another. And if they're not interacting with one another, then we can assume that their behaviors start to become more ideal. When they're at high pressures, they're compacted, right? So if they're compacted, now they start interacting with one another. So as we're moving down the graph, we're seeing that there's 2 issues. One is more non-ideal because you're compacting them and now they're feeling each other. But then you're also doing a better adjustment for that by making higher temperatures. And so now they don't feel each other as much. So the real issue here is that molecules have intermolecular forces. And so while I'm going to talk to you about these specific high pressure, low temperature situations, what I really want you to understand is that the kinetic molecular theory doesn't really work well for gases. So let's go through kinetic molecular theory, and if you don't know it, you need to start jotting these down. You do know them, but maybe you need to identify them. So what's one of the things that we have to make assumptions for gases? What's one thing? They really have no volume. They just don't take up space, right? We talked about that because of the 0.0084%. So they really don't take up much space. Most of the space that they occupy, we say, is empty space. The other thing is that they're very far apart from one another, right? So we say that they don't really interact with one another. We say that their collisions are elastic. So remember we talked about that. So they bounce off the walls and each other, and they don't lose any energy whatsoever. When in reality, we know that there's friction and there's other things that could inhibit their motions. So the last part too, there's a few other postulates that do sort of make sense, but the one that doesn't at all is that they have no intermolecular forces of attraction, ever. So when we use the kinetic molecular theory, we're saying that gases never feel forces of attraction onto one another, which is impossible because if that were true, everything would exist as a gas and we would never have liquids, right? If gas molecules never found each other and became connected through bonding of some sort, then we would never liquefy and condense things. Everything would just exist in the gas phase. So that's the main problem with kinetic molecular theory, and then this is that molecules do in fact feel each other. And when they feel each other, then it causes problems with the PV equals nRT. So that's what I'm saying here. When the temperature gets high, we become more ideal because they're moving further away from each other. So even if they had intermolecular forces, they're moving so fast that now they really can't feel each other. So that's ideal. Not feeling each other is ideal. Get it? So here's this volume adjustment for gases at high pressure. So don't read this, just listen to me and then I'll read it for you. So when you're under high pressure, this is that what I just said to you, is that you're compacting the volume of the molecules and now the space that they occupy needs to be accounted for. Right? So just envision, Mike, your whole group, you don't feel each other, you occupy no space. I'm assuming your space is negligible in this room. I take you 4, I put you in that cabinet. Look at that cabinet. Will your space, will your volume now be considerable? Yes. So I have to get rid of that and I have to subtract that out. That's all this is saying. So there's a volume issue for high pressure. So when I ask you on the exam, explain why high-pressure situations create a non-ideal gas. It's because we assume their volume, we assume the volume in the PV equals nRT expression is empty space. That's what we assume. But in reality, the molecules do in fact occupy a volume under high pressure. Why? Because they're compacted. So that's what this says. The ideal gas equation assumes that molecules do not have their own volume. That's your first sentence. That's specifically true in the PV equals nRT equation for volume. The volume of gas particles are negligible when compared to the overall volume of a container at relatively low pressures, 1 atmosphere. But as soon as we get to that greater than 5 atmospheres, we end up at a high pressure system. The molecules are compressed into a much smaller volume of space, and the volume occupied by the molecules becomes significant. So we have to account for them. So this is just a visual representation of molecules, but I use humans, and I compact you, and now you occupy space. Right? So what you don't want to do is listen to me and be like, yeah, I get that. And then Friday comes and you're taking your exam, and for the first time, you're attempting to write this essay. Because it doesn't come out the way you want it to come out, right? So at minimum, before Friday, you should write out why gases don't behave ideally under high pressure and why they don't behave ideally under low temperatures, and discuss the pressure and volume issues for both of them. Then when you get it on the exam, because I'm telling you you're getting that you already know exactly what you want to write. And then you can check your work with what I'm giving you right now and make sure it makes sense. So this is the equation, but you'll never use it. It's just showing you that the actual volume that we're measuring here, you have to subtract out the volume of the particles, and that would be the actual volume that you should use in the ideal gas law. So the volume that you measure is actually here, have to subtract out the particles. So your ideal volume will be less than what it should be or what it was measured as. Right? So the theory questions that you're going to see are multiple choice. And they're not going to ask you for a number here. They're going to be something like, is it equal to, greater than, or less than the volume of the ideal equation? And then you have to manipulate and think about what's actually happening with the molecules in the empty space. Just remember, PV equals nRT is for empty space. Got it? All right, so here is our force of attraction between the particles. So we assume for kinetic molecular theory that they have no forces of attraction, but in reality, they do, in fact, attract one another. So what causes a problem there is for our pressure. So we already talked about volume, right? Volume means we have to take into account the molecules themselves and their size. Now we're going to talk about pressure. So before we read this, I think it's best if we do a little example. So, Brandon, would you like to help? Okay. Anyone else? Great. Julia, would you like to help? Sure. Raj, you're in it? Sure. We'll just take you three. Okay, so I don't know. I guess I'm not allowed to record you guys. Am I? So here's our analogy. We're just not going to use names, although I just said them. Okay, so Brandon, you're going to stand here. Oh, wait, I just said we weren't going to do that. Mandan. And you're going to stand there like that. And then you, child, will stand there. And then we're going to put our hands up. You. Okay, so punch us.
Wait.
Yeah, Raj, there you go. Okay, so I'm the walls of the container. Come on, be a molecule. Oh, gosh. Didn't know this is serious. All right, so keep going. All right, those are the molecules, right? The two inside people are the molecules here. And then we are the walls of the container. So do we feel pressure? So under the ideal gas law, this is what we assume is happening, is that molecules are hitting the walls of the container, and this is the pressure they feel. Okay, pause. All right, so now link arms. Both sides. What am I indicating is happening here? What just happened to them? They have intermolecular forces of attraction all of a sudden. Before this, they had no intermolecular forces. All right, now punch the walls.
She can't.
Raj, you gotta be stronger.
Be stronger. All right, so what do you notice is happening right now?
It's harder for them.
The pressure is, what were you saying?
Well, it's harder for them to hit, so the pressure is decreased.
Yes, it's harder for them to hit because the pressure's decreased. Why is it harder for them to hit? They're together. So there's not this outward hitting. There's like this trying to hit the walls of the container. So they have inhibited motion, and therefore the pressure on the walls of the container is decreased. Try it again just because it's funny. Get strong, Raj. All right, thank you. Let's give them a round of applause.
Yeah.
Now you have that visual. All right, so that's exactly what this is saying. So you know why volume is adjusted, right? Volume because at high pressure, molecules now occupy space. Now you know what happens to the pressure. We assumed that the pressure is the pressure exerted by all the molecules without any intermolecular forces. When do intermolecular forces show up? When you're at what temperature, high or low? Low, because what do they do at low temperature? They slow down. And now all of a sudden they're like, hey, I can feel you. Oh, and then they have intermolecular forces, right? So then the pressure is decreased. So it says, when gas particles are very close together, the pressure they exert may be less than what the ideal gas equation would predict. Neighboring molecules exert forces of attraction on one another when they are very close. Such forces pull a gas molecule in the direction opposite to its motion, so it impedes it from hitting the walls. This reduces the pressure resulting from impacts with the walls of the container, so you have to be able to describe that. So now again, how do gases behave non-ideally with pressure? How do they behave non-ideally with volume? So this is just showing you the example that I just did with humans. Same thing. And then this is the adjustment for the gas, for the pressure in the ideal gas law. So to come up with the pressure for the ideal, we come up with the measured pressure. Now the measured pressure that we're measuring, is it equal, less, or more than what it should be? What did we say? The pressure that you're measuring, my literal hands feeling his punches, once he has intermolecular forces, I'm feeling less, more, or equal to the ideal gas? Less, right? So that's why I have to add in what I'm missing out on. Do you follow that? Like, had he not been inhibited, what would his pressure be? And that's what the ideal gas law is going to be. Ideally, without any of these alterations, without intermolecular forces, without high pressure, without low temperature, what would the pressure be? We don't have to use that equation. Just realize the greater than, less than, or equal to scenarios. So how do they behave non-ideally at low temperature? We just said this. Kinetic energy is low at low temperature. Therefore, they slow down, and they can interact with each other more. Key things are intermolecular forces are taking over and impeding the pressure, or decreasing the pressure, sorry. So the ideal gas law assumes that gases experience no intermolecular forces. That's kinetic molecular theory. At high temperatures, the kinetic energy of the particles overcome any intermolecular forces because they're so fast, they can't really come in contact. At low temperatures, gas particles move slower and are closer together, and attractions between molecules exist under these conditions, right? The closer they get, they feel each other, and they become attracted to one another, like humans. Like Patrick Swayze in Dirty Dancing, and he's dancing with Baby, and how do they end up falling in love? Because they're so close and they're dancing all the time. Do you know that analogy? You just saw the Super Bowl. How did you not relate that whole commercial? You don't even know what that commercial's about? What commercial?
Is that the one where she pours the water on?
That's when they're dancing, and there's the whole lift at the end. That's Patrick Swayze and Baby.
Oh.
You don't get the reference, do you?
Well,
Oh.
I know that, but like, what's the movie with the water?
I don't know that I saw that one. But you guys, did you understand that reference or no?
On the chair.
How many of you understood the dancing references?
Oh.
Like
I never seen a movie.
4 of you.
Wait, hold on.
Wow.
What's the movie where they're
I gotta pause this so we can sidetrack. Okay. So here's the van der Waals equation. And van der Waals is literally just the same name as London dispersion forces. So someone might say van der Waals forces, and someone else may say London dispersion forces. Same thing. It's just interactions with molecules. This specific equation you'll never have to use, so don't even worry about it. It's just there is an equation to give you the ideal gas law. So non-ideal behavior and condensation. Condensation is going from which state to which state? Gosh, I hope you know.
What? Sorry.
Get it?
Yeah.
Get it? What is it?
Gas.
Oh, phew. Yes. And then what is it called when it goes from a liquid to a gas? Evaporation or vaporization. No, that's good. Yeah. Vaporizing, evaporation. All right, we need to know those like freezing and melting and evaporating and then condensing. All right, so when molecules condense, it's very easy for them to condense under high pressures, right? And low temperatures. Same scenario. Why? Because they feel intermolecular forces with one another and then they're able to condense. So that should make sense to you. How do you get liquid nitrogen? There's not an environment where they just make it icy, super cold. I mean, of course, I guess they could conduct that, but they just pressurize it. If you pressurize it, you can force the intermolecular forces to attract to one another, and then they're forced to condense, right? You just shove them so close to one another that they have no other option than to create intermolecular forces. Non-ideal behavior and condensation, I'll just read this quickly. It can occur rapidly when the temperature of a system drops, obviously because the molecules come into close contact with one another and they stick together, or at high pressures because they're so close to each other that they're forced to feel intermolecular forces and then cause them to condense. Everybody good? Okay, so can you take out your multiple choice?